I spent a long time as a building surveyor.
Yeah.
So I qualified as a building surveyor, and I'm a chartered building surveyor. That's really was my core role. So looking at buildings, improving buildings, and ultimately retrofitting buildings towards the end of what I did. So yeah, I came out of uni as a fresh grad, and I went to work for a building surveying practice, surveyed buildings for a number of years, from stock condition surveys right through to post office, banks. Then I ended up working at the Army and the RAF on the Ministry of Defence side of things. So yeah, I've covered homes, hangars, you name it, all with a view to improving either their performance, inside, outside, energy performance, you name it, cyclical maintenance. I spent a long time dealing with buildings that aren't perfect, which is pretty much still what I do.
So buildings that aren't perfect, you're talking retrofit or existing buildings?
Retrofit, bear in mind, 20 years ago when I came out of university, retrofit wasn't really a thing. We were improving buildings, we were insulating buildings, but the kind of retrofit, putting it all together, that didn't come to quite a lot longer after that, in any number.
In an organised way, right?
Yeah, we were just doing lofts.
So why do you care so much about buildings?
Why do I care so much about buildings? It's a good question. I think I've always been into looking at how things work. If something doesn't work, then why doesn't it work? But usually with a view to kind of, if I find something doesn't work, how do we get it to work? I think buildings, we can go around pretty much any building that you go into and you can find something that can be improved. So what happens in the building is really important. And you go in a bad building and you can feel it. We came in here today. First thing I did was complain. It's very warm in here, isn't it? And it affects how people are. And, we hear the horror stories around mold and health problems and things like that. And that's the extreme end of it, unfortunately, getting more extreme and more common, unfortunately. But anything that you do in a building is affected by the building itself. So I see buildings as a place where we spend a lot of our time, and there's always room for improvement in buildings, right from the old buildings like we're in now to new homes that are being built. So yeah, I go with a meal with the missus, and the first thing I'm doing is looking at how a building can be improved. It's damp on the ceiling, that fire exit box, things like that. It's kind of something that you develop and you never switch off. And it is fault finding ultimately, but fault finding is useless unless you can kind of fix it. And I think that's what I like to do: find something wrong, fix it.
So at the moment you're a professor at Salford University.
Yeah.
But what do you actually do?
My title is Professor of the Energy Performance of Buildings. Okay, so that's what my chair is. What do? I don't teach a lot. I teach a small amount on the building surveying course and the masters that we have in sustainable buildings, which I enjoy. 90% of my time is researching how buildings perform. So the history of kind of what we do, if you like, which will tell us kind of what I do day to day. When I started 12, 13 years ago, we had a project that opened on the day I started, which was called Energy House. So Energy House is a 1900s Victorian terrace in an environmental chamber. So a full-size building, 1.5. So it's got number 1 and number 3, exactly as you'd find out in the field. Built using reclaimed bricks, recycled materials, and we've validated that it performs the same as a house outside.
And so this house is built inside of a larger warehouse or a larger...
Absolutely. So it's in a large environmental chamber, but the bricks are 100 years old, well, more now. The materials that we use to construct it are all consummate of the materials that would be used at that time. So it behaves the same as that building. The thing that makes it unique and globally unique is that we can alter the temperature and the weather and the climate, if you like, it in that chamber. So we can go down to -12, up to +30, wind, rain, snow, solar radiation, and we can put all those things on in any quantity we like. So you're talking really the Northern European climate we can recreate in there, certainly the UK climate. And the whole point of that building was to examine retrofit in the UK at the time. And we've examined retrofit. We've pretty much looked at everything that you could put on, change, alter, install, or take off a building. So right the way through to full deep retrofits, with walls, floors, ceilings, windows, doors, heat pumps, you name it, the full package of work, right the way through to looking at curtains and carpets and the smaller but more cost-effective energy-saving measures. It's a mix of funding between government funding, academic funding through the university, and commercial. So about 60-odd% of our work is commercially funded through industry. So whether that's boiler manufacturers, energy suppliers, building product manufacturers. There's a really good mix of people, and right down to one-man bands, literally out of garages and sheds through to the multinational, multi-billion-pound companies. And I think it's a really healthy mix.
So can you give me an example then of things that you've discovered from the house project?
Yeah, I mean, discover is a strong word. We didn't find graphene. What we do find a lot is things that do work and things that don't work, or don't work as well as perhaps they could or should.
Okay.
So, but part of the fun, I think it's fun, is not also finding something that works and confirming that it works. It's nice to find things that work slightly better, because for the environment that kind of helps, and it's pleasing. It's nice to see someone happy with their test results. But it's also good for us to find things that don't work, so that they don't get installed in buildings, and they don't get installed at a very high cost and make very low savings.
So give me an example of that then. What historically do people believe, or did they believe, that would work really well in a retrofit? Through the research that you've done, it's actually negligible.
A paper we published, I think 7 or 8 years ago, I guess you can put a link to this in the description, looked at thermal paints. Okay, so coatings that you put onto a wall and ceiling that claim to make some pretty significant savings. So some of them were advertised with savings, if you paint all your walls and ceilings, with savings up to 35% of your energy would be, heating energy would be reduced. An incredible amount of savings. We found that when you compare them even to things like vinyl paper, wallpaper, EPS, very thin EPS sheet like we used to put on in the 70s to stop condensation, they're nowhere near even that. The savings, we found paybacks up to 200 years, because the sheer amount of paint you need to put on a wall to make the saving, the simple fact that they didn't save hardly anything from a U value on a solid wall was quite stark. So, but being sold in quite considerable numbers. Now, thermal paints do have some use, and that's to lift the surface temperature of the wall. So in condensation cases, they can often help. They provide this kind of very thin layer of insulation, which can just bring that wall away from being a condensation risk. But to say they're going to save you a great deal of heating energy, well, your listeners can read the paper. Yeah, I'm not. So things like that, I'm a big believer in proving things don't work if it can help society find out that it doesn't work as well.
What have you found works really well? What stands up well? And
so again, there's been no graphene moment. There's no eureka moment. We found a lot of things that work as they should, and to me that's a good finding, because you're heavily involved in the design of buildings, Darren. And when as a designer and an evaluator of a design, when you've got some surety and confidence that what you put in is going to work, that's good. And that to me is a good finding. There's been some things that have surprised me in a nice way. So there's a product called Thermosil, which is by a local innovator, and Thermosil is a window board that you put across. You take off your old window board, a windowsill, some people call window ledge, some people call it, and then you put on this sill. As we design buildings, generally in the UK, we have a radiator underneath the window, which is fine. It's convective flow. That's kind of how it should be. What Thermosil does is channel the air, the warm air, the rising air, in front of the window, lifts the surface temperature of the window, creates the same effect as a mini air curtain. So when, for your listeners, you walk into Marks and Spencer's and you get the air curtain effect, and it stops the heat or the cool leaving the building. So that's the effect that they claim to have. And it's counterintuitive if you think about it, because you're funneling heat next to a cold surface. So I had some thoughts, but as a scientist, you should put them to one side and just do the experiment. And my instinct was it wasn't going to work. It did work. And the savings aren't, colossal. And again, there's a paper just gone out on this topic. And if you Google it, you'll find our findings. But, over a U value, it's a couple percent. And it changes at different points in the window and stuff as well. Again, when you look at things like condensation, that can have quite a marked effect, and if you can turn a house that's got condensation problems on single glazing into something that doesn't, then that's a win as far as I'm concerned. But it was counterintuitive, and I explained it with physicists that are far better than me. I'm a building physicist, I'm not a physicist, and I've explained it to engineers who are far better than me, and it's counterintuitive. But you've got to do the test. and you know, we found it worked, and we've been working with Thermosil now for probably about 7 or 8 years with a view to providing data to get them through SAP and things like this.
If someone's looking to make savings in their energy bills, make a difference in the amount of CO2 that comes from their own carbon footprint, what would you suggest would be the top 3 or 4 things for them to look at?
Which is a question I get asked all the time. So it totally depends on the house. It totally depends on the person as well.
So if we just take the average 2 up, 2 down Victorian house, and then maybe end with a 1990s style build terrace.
To me, many people will disagree with me, constantly do. It's about getting the fabric right first. You know, we can talk about heat pumps and changing boilers and controls and things like that. Unless you've got the envelope in a better shape, then doesn't matter what heat pump you're putting in, you're going to be heating Manchester rather than heating your house. But it's a big cost. You know, so loft insulation, probably the most cost effective, bang for your buck. Floor insulation is probably the least bang for your buck. And solid wall insulation, if we're going down that road, costs a lot of money. But for some, it's prohibitively expensive. For grant funding stuff, it's obviously different. Then it's about minimising wastage. So, you know, look at, if you have got a gas boiler and you're probably not looking to change it because you haven't got that much money, then controls are a cost-effective way of just reining that in. You know, and if we can heat the rooms where we are, it doesn't take a rocket scientist to figure out that it's going to save you money. So TRVs, you know, thermostatic radiator valves, even the manual ones you can back off in the rooms you don't use that often. Caveat that with not too much, because then you end up with even more problems around condensation and mold. And then you can step up a level to the kind of things you can control by the hour, by temperature, which, you know, they're nice devices to have because you can control. So I have them in my house. You know, the kids' rooms get warm at night, but when they're at school, what's the point heating them? So, you know, controlling that, even if you have an old efficient boiler, if you can control it well, it's going to save you something. Then you start to look at the heat source, and we get to our air source heat pump challenge of what do we do. But if you have insulated it, you can and you can put a slightly smaller one in. But if you haven't insulated it, you're looking at a bigger one. And again, that's a challenge. But many people will say that, you know, that is outweighed by the 3-to-1, 4-to-1 ratio that you get from a cop of a heat pump. And then people will disagree to say that you might not get that cop if you haven't got the insulation in place. That's a detailed chat, you know, and it's not a chat that you can have about an archetypal house. Every house is different, and we need to really understand that. Every house is different. Every occupant's different as well. If someone who sporadically occupies a house might not get some of the benefits that someone who's living in a house all day, every day, you know, someone who's retired. And I think I was having this chat with someone the other day. I'm not copying out your question here, I am a little bit. Retrofit needs to be a bit more personalised. You know, I was having this chat in an RSCS meeting the other day about how we survey homes. And I think unless we can get to nail the problem of what does that person want out of a retrofit, you know, we've got to stop seeing the house and maybe seeing the person with it as well.
I think what you're saying there with reference to using a broad brush approach to retrofit, and you need to do this, this and this, whether you live in this type of house and you have this type of lifestyle versus someone else's, I think is 100% correct.
We decorate houses to our own taste and our own living styles, and we equip them with technology to meet our own lifestyles, our Alexa and security systems and this and the other, and yet sometimes I think retrofit gets seen as a one size, which it can be for a loft insulation.
But you see, that's the downside of the soundbite society that we live in, is what people are chasing is this soundbite to say, do this, all your problems are solved.
It's not I wish it was that straightforward, but on the other hand, if it was, then I wouldn't have a job. So we get asked to come up with silver bullets in life across many, many different things, whether it's education, lifestyle, diet and fitness. Everyone wants this kind of magic cure. You know, air source heat pumps get banded around a lot for this magic cure. Now, don't get me wrong, they're good and they are super, super, super efficient. But that without some insulation being fitted across the stock as well, then we are heating the UK rather than our homes, and just doesn't add up, does it?
So we've talked really briefly about house number 1. What's the actual name of it? I call it house. When we opened, it was Salford Energy House, and it still is Salford Energy House. We've started to call it Energy House 1 only because
we built Energy House 2, which leads nicely on to what we do there. But joking apart, there was a bit of a shift. So Energy House was with us first of all, Energy House is probably our busiest asset at the moment. Retrofit, we discussed it then for 10 minutes, we didn't get to the end of it. It's like we don't know what the answers are yet. It will always, I think, for the next 15 years, be our busiest asset. Retrofit has not been answered globally, and certainly not in the UK. There's more things we can do. There's smarter ways of doing it, there's more efficient ways of doing it, and there's cheaper ways of doing it.
It also feels like to me that there are things that we can use that have not been invented yet or been brought to market.
We thought that when we'd achieved flight, nothing else could be done. Okay, if we stop here, we could be missing loads of stuff. Well, we could be missing the silver bullet. I don't know what it is, but we could be missing it. So we aren't stopping. It is very much our busiest asset, and the guys down there are mega busy trying to fit in all the tests because there's so much demand. Government demand, commercial demand, academic demand, right the way across the piece. It will be busy. We noticed 6-7 years ago now, Will, who's my boss, and I, that we should probably make a shift and try and do something a bit different. Sometimes you got to move. And Retrofit did go through a bit of a slump, and we thought, okay, well, what we need to do is we need to branch out from the UK. We need to make somewhere more flexible, and we probably need to look at newer and more innovative types of housing, because we got part of the way answering Retrofit, and I think we've done, the team down there, led by Dave Farmer, have done an absolutely magic job since I kind of handed it. But we're still nowhere near the finished product. But we needed to kind of shift. So what we did is we came up with some feasibility studies for the new building, and several versions of that later we came up with something that we could actually afford. So we went from having a full street in a chamber with trees and everything in it. I seem to remember. We kind of value engineered it down to something we could afford, which is still an enormous place. So we got enough room in 2 chambers to build 4 homes. So we have 2 chambers. You can fit 2 detached family homes in each one. So an enormous place. And then we went to get the money. So we were funded part from ERDF, European Regional Development Fund, the last batch of that money. EFKI, as it was now the Office for Students, a significant amount in, and the university put a significant amount in as well. So £16 million later, we built it during COVID, which was interesting, and we finished on time and on budget, which was good. It's an absolute win, and it worked. So the problem with Energy House when we first opened is it didn't work as well as it could.
In what way?
We went on, let's call it HVAC principles rather than refrigeration principles. So the controls were difficult. There was for the technical listeners, there was a big hysteresis in what it was achieving. It was bouncing up and down. The temperatures were bouncing up and down. So we refitted the system. We went for more of a kind of cold room refrigeration style approach with blast chillers and things like that. And yeah, it's great. Now works within 0.5 of a degree. It's a brilliant system.
So for those people that don't understand the technical element, what does that actually mean?
We used, let's call it an air conditioning type approach, which we've got, something somewhere in this building out in Central Core there. What we moved along to was the ability to use what we call blast chillers. So when you go into walk-in freezers, that's the kind of approach that we use for going, 5 and less is what we used those for. So that gives us a closer control. So we can recreate these weather patterns within 0.5 of a degree accuracy. So
that's because you're getting the temperature down a lot quicker, and the temperature is maintaining that low.
Yes, and there's less kind of frosting on coils and stuff like that. So all physics experiments should be well controlled. So what we do in there's a well-known kind of scientific principle called 1 factor at a time. So you change one thing at a time. So we add insulation, that's our 1 factor. We change the weather, that's 1 factor. We change the windows, and then we go through and we do it step by step by step. Then we get a nice graph that says these are what each savings made. And it's a really sound principle. It works really well. Everyone can understand it, and it's pretty easy to communicate. Whereas models, they're a little bit less easy to communicate. So we had lots of learnings from Energy House. We need to probably build something bigger, more flexible space, everything to build that 2-bedroom, 2 up, 2 down terrace came in down a corridor through a set of double doors and into the chamber, because the chamber was already built. It was an old physics facility. So everything had to come down wheelbarrows and
really
trucks,
limited.
basically. Yeah, it was really limited for size. So Energy House 2, we had to totally change the way we thought about things. So we wanted a broader climate. So we wanted to go down to minus 20 and up to plus 40. We can go higher than plus 40 with solar radiation, but that's the air temperature. And arguably we should have gone a bit higher because the climate's changed in the last 10 years since we kind of started planning that building. We were okay. The solar radiation rigs take care of a lot of that. If we were going to do it again, I probably want to maybe go up to plus 60 air temperature, just to give us some breathing space up at the top end of the climate predictions. And we built it with a view to a big hangar with cargo doors on the back. So the cargo doors will take any truck that can move on the UK motorway network. So when you're talking about volumetric and modular, and even things like, large caravans and stuff, which we've been asked to test in the past, anything can fit through those doors, basically. Very high, very wide, and very capable of taking the traffic. So we wanted something flexible where we can literally come in, build what we want, a few years, tear it down, ship it out, build the next thing. But we also wanted something real. So the reality of those chambers comes not only from the size and from the climatic control, so wind, rain, snow, solar radiation, but also the fact that when you build a house, you put it in ground. You don't build it on stilts or on a little concrete thin pad or something like that. It goes into soil, and the soil bears the load and it bears some of the heat transfer as well. So we had to make it super realistic, but we didn't want it to be soil that was affected by the outside. We wanted it to be soil that was, let's not call it climatically controlled, but that was altered by the climate in the chamber over a period of time. So we have a 1,200 millimetre, basically a swimming pool full of soil that's really well insulated. It's got local soil in. The real soil, 6N grade soil, will bear any building that we put into it, and obviously that's fully insulated, fully reinforced. A couple of £1 million went in just to building that no one would ever see. I've seen it, and the guys who I work with have seen it because we've been down in the mud putting the sensors into it. But no one else would even know that was there, for instance. So when you look at ground heat transfer, underfloor heating, and things like that, we've got sensors under the buildings that are kind of looking at that. So that adds that depth to it. So and then you've got the size. We need to get things like cranes, timber frame erecting, machinery and stuff like that in there, which we do, and which we did with the two houses that are in there now. So yeah, it was a very complex engineering task. And then you throw a problem, the design engineers, to say this huge volume of space. So that's two houses plus a few meters, probably 3 or 4 meters around the outside, plus at least 8 meters above them, all has to be conditioned with stratification of less than half a degree and control of better than half a degree. And then you talk about humidity, then you talk about putting wind in there, and you talk about putting solar radiation in there, which are all on mobile rigs because we don't know what shape anything's going to be. Then you want it to snow, then you want the chamber to deal with snow. It becomes, from something that seems really easy, something that's bloody complicated, to be honest. Just getting snow in there is an immense chore.
So you're talking real snow here. This is not the fake stuff.
So we were complimented by the guys who installed our snow machine, and they said, because these are snow machines off the Alps. So the Klenko, they're called, they make the snow machines that you see on the Alps. They're exactly the same. We just provide the temperature and humidity that you would find on the Alps. Then they just come and put this, the snow machine comes in and does as it would in on the Alps. So snow machine, for those who haven't operated snow machines, it's a fairly straightforward principle. It's compressed air, compressed water coming out of a very fine nozzle, a nucleating nozzle, which creates a very, very small drop of ice, if you like. And then there's something called a hang time. So you put it high up in the chamber, and as it hangs, it forms little snow crystals on the way down. So it's same as, not as high as the clouds, but kind of getting there. Yeah. And yeah, they said, this is powder snow. This is snowboarders would pay to come and kind of roam around in this stuff. And we've done studies. We just put a paper into a conference looking at Arctic research bases. And we looked at the literature, we look at the conductivity of snow, and ours is pretty much nailed on. But no one's done a great deal about how much snow insulates a building, which it does. But then it starts to turn to ice and the phase changes, and then it starts to do something a little different. And then when it melts, it does something quite different. So But all these things we don't know about until we can do it under controlled climates, because we don't get the chance to let the snow sit there and do a co-heating test in the building and stuff. So yeah, when you've got things like that you've got to contend with, lots of heads start getting scratched, and it becomes complex, expensive, and difficult to design, I would say. So we got through it, and it does what it does.
What surprised you
about the completed project?
Yeah, I think about just the completed project because this House 2.0 is new build.
Yeah, absolutely.
So what surprised you?
With our findings? First and foremost, the building works, okay? And that surprised me, because it's never been built before. In the history of mankind, no one's ever built that shape, size of buildings where you test buildings inside. So someone explained when we looked at Energy House 1 as the HVAC principles. A cold room has dead cattle in it, okay? You freeze the cattle, that's it. Pretty much that's the heat energy taken out of those dead cattle. Unfortunately, Energy House 1 and Energy House 2 has very much live cattle inside, with the dynamic loads from the chamber, the heat burden of the heating systems of the housing, people, metabolics, the lights, everything else. We have got live cattle in our cold room, and that is a problem. So the machinery, the HVAC equipment has to be able to constantly take readings and react to those live cattle, those live loads, if you like. So we did a load of CFD around it. CFD's great. My thoughts about modelling, it's good for some stuff. Some of it's just made up numbers. And yeah, we were sure it was going to work, and it did work. And that was a big finding for me, first and foremost. So after that, we then went to an open competition about who was going to build homes in there. So we had a free and open competition, because it was funded by the ERDF. So we had to have it open, and they had to whoever won had to bring in SMEs, small to medium enterprises, in there and work with some of the novel stuff. It couldn't just be a big installation firm or this only. We had to work with some small companies as well, because that's the way you should do business.
So what you're saying here, just to clarify here, so you've got this big test chamber with the ability to change the weather. We'll say at a push of a button. I know it's more complex than that.
Well, a click of a mouse. Yeah.
And then what you did is went onto the open market and said, right, who wants to come and build something?
Yes.
Or who wants to come and build a house in this space?
Yeah.
And they needed to put an application into you and your team?
Yeah, it was a fully open and transparent process, and we had several applicants, and we judged it by...
What did you have?
More than a handful.
Okay.
You don't get a million, for something because they're going to have to come in, pay for the house to be built, and understand it.
And what were you looking for? What was your criteria to, yes, these are the organisations that we want to work with? Impact.
So how do we get our message out? Pointless doing research if you can't get it out. So you want someone who's got good contacts with the press and industry as well. Pointless keeping the findings inside that chamber.
Yeah.
Carbon. You want good carbon savings. You want people who work with SMEs. You don't just want to work with big multinationals. They have to have some. And then we're looking for innovation. What are you doing different? There were a couple of other.
Go back to just to dwell on the SMEs. Why is it important for a large organisation? Because it's not going to be a small house builder, is it, that's going to have the money to do that.
Yep.
But why is it so important to have a large organisation connected with SMEs?
Because I think it drives innovation, and SMEs do innovate a heck of a lot, and they're very nimble, they're very lightweight, they can move quickly with technology, and I think unless you don't put the two together, you're on a highway to nothing. You really, really are. And we see some of our most interesting, novel and impactful things come from SMEs. Now, clearly, we do with huge manufacturers as well. And the house builders really put it all together. They will deal with innovators, but, they need some innovation to come to them as well.
Are you happy discussing the house builders that were successful in working with you?
Yeah.
So, and also what they have brought to the table?
So the two house builders that we have now in Chamber 1, our first chamber, is Bellway Homes, and then next to them is Saint-Gobain, the product manufacturer working in partnership with Barratt Homes. Barratt and Bellway are competitors, as you will know, fierce competitors, I'm sure, in the commercial marketplace, and oftentimes probably don't share a lot of information between those two companies. But when you cram someone into a chamber to work together, which they actually suggested, not me, and they're sharing ground workers, timber frame erectors, scaffolding, the things that go on a building site. And then they sign an agreement to say they'll share all the data with each other. They agreed not to test the same technologies because that just would have not been a good use of anyone's time. They agreed to publish everything they found into the public domain where the reports are now, and also to actually have a genuine partnership and develop this as a project. That's unusual. You know, the house builders tell me that if this was real life, if you like, if this was a green site, they'd be barbed by a fence up down the middle and there'd be no talking across the line. You know, they're commercial outfits. So I think when they've got this aim, which is to create something that they can use for the future home project standard, if you like, and you see that that's the length they go to, you know there's a risk there. You know that they're doing that because it's a difficult problem to get over. And they actually work really well together. There's nothing between them. They've got the same goal, really, to get good quality housing that meets regulations and people are happy with. You know, there's nothing. They brought their expertise. You know, let's not forget, you know, the house builders build a significant number of houses up and down the country of varying different types to the regulations, over and above when they need to, and they understand the house building sector. If an academic designed the house of the future, well, I think we'd be in a different place. I think they look a lot different, but it wouldn't be representative of what was on the housing estate. They've built houses that exist on the sites now that people are buying and that they will build in 2025 when the regs should come out. So, yeah,
Talk to me about Chamber 2.
Chamber 2 is currently where we've got some more of our, let's say, R&D based projects. So I think the view is to build 2 houses in there probably next year. Now we're looking at doing that might reflect some of the older housing stock, yet to be decided. What we have in there are some interesting projects. So we just finished a project with an outfit called Mat Zero. So Mat Zero, we're looking at the UN issue a standard tent to refugees. Very good quality. It's a tent, and they're in some very distressed regions of the world, both hot and cold, and people living under dire circumstances all around. The average time that people spend in there is multiples of years, not multiples of months. And 4 or 5 people will live in these tents, these canvas tents. And they heat them by lighting a fire outside and then moving it inside sometimes. And that's obviously just a death trap all around. Fires, suffocation, you name it, it's just terrible. So Mat Zero came up with a kind of carbon heating mat that works using renewables on the outside of the tent, which feeds a battery that they can use for mobile Wi-Fi and to charge phones and torches and things like that, which heats them as they sleep in their beds at night. Obviously, a much, much safer way. So we helped Mat Zero develop that product and do the testing, and it was a product that you know was going to be used for something that was really genuinely good. And I like projects like that, and we give our time free for stuff like that, because I think if we didn't, then how would a small company kind of ever get that lift off that it kind of needed? And they were great to work with as well. Very technological and scientific, and put the hours in to make it right. To one side of that now, we're working with a firm who insulates conservatory roof. I think it's one of the larger firms that does it. Big benefits in terms of livable qualities of conservatories, which we've all seen overheat and underheat and things like that, and they just become this hot box or cold box on the back of you, and they can be occupied for several weeks of a year in a comfortable condition. So, and there's an interesting aspect that we're going to look at in that, in terms of how we model conservatories and the heat gains and heat losses that change dynamically during the year. So we've really characterised this conservatory well. U values, air tightness, and whole conservatory heat loss, with the view to making a super good model of that. It's calibrated to within an inch of its life, and then we see kind of what difference that makes to heat injection and heat rejection from a home when the doors are open and doors are closed, because regs say we need to put the doors on, but often they get taken off or they get opened, you know, as you would. So that's a really interesting piece of research. So we got that. We got the thermosil cabin there, which is a site cabin that we just transformed by filling one of the walls with sand and making it into a solid wall, and then putting the windows and stuff in for the thermosil experiment. That was key to answering all our scientific queries around thermosil, because we needed somewhere super stable. You try and do this stuff out in the field, and the noise, the noise on the measurements is really, really difficult to work. And then larger building in there is by an outfit called Vector Homes. So Vector Homes is a spin out from one of our neighbours just that way, Manchester University, the Graphene Centre. So Vector using graphene to reinforce the insulation inside. They have a panelised, very lightweight panelised structure. I believe everything that weighs less than 25 kg. So there was no cranes and no forklifts and stuff. It was all, if not manually handled, certainly didn't need large cranes to kind of build. And that was the first house that they've ever built at Vector Homes. I think it was a learning experience working with the construction industry and engineers to one side. It performs in line with how it should perform, so that they are aiming to produce a very low cost and very low cost running and low cost building, low cost labour to get a very, very cost effective home.
So talk to me about the home energy model.
So we've had experience with so for your listeners, the HEM is a new way that we're going to start to model energy performance in buildings in line with the Future Home Standard. I think from what I know, it will be used for retrofit as well. I think it will replace the standard model ultimately that we use for existing buildings. But it takes us from a point where we're looking at monthly figures to where we're looking at half hourly figures. So we've gone from 30 months to 30 minutes. And that is a dramatic transformation. I think it's a bold move by government. I think it was a move that I was expecting they would do, but I think they've done it quite quickly. I think it's an adventurous step, but I think ultimately it's going to be one that's a useful step, because the buildings that we live in, particularly the future homes, won't be steady state buildings. They'll be very dynamic, and the energy systems will be very dynamic. When you've got things like EVs, PVs, batteries, heat pumps, whatever's doing your hot water as well, all kind of interacting with a tariff that could be operating on a half-hour basis or even a minutely basis, when we get to that point. Then that becomes a bit more complex than monthly figures. And, I understand SAP. I get what it does. I'm actually quite a big fan of SAP. I sit on the SAP Scientific Integrity Group. I think it does what it should do, but I think it needs to change into the way that the current situation is going to change into, and it will be dynamic. And I don't think SAP could have taken that big shift.
There's always a bit of fear around it as well. Yeah. Clients that are coming to us quite anxious, asking us what they need to do and so on. Just wonder what your thoughts would be on that. Someone that feels quite concerned about getting hit with something that's unexpected, and it's always cost-based. It's always, this is going to cost us a shitload.
So I think my advice would be either themselves or through a consultant or an expert, build some models of what you're currently building. But they must be anticipating that things are going to change. The Future Home Standard now is out for consultation with two options. I think there's a conservative one, there's a more adventurous one. I don't know what's going to get picked. Historically, we've kind of gone with the more conservative stuff. Conservatives have gone. So do we end up with a different option coming out of the mix? I don't know. And the second we try and play the game of what government are thinking, that's a dangerous game to play. We don't know what's going to happen. There's a model there that we can use, and that's great. They've pushed the model out the door. It's got some issues, and we found some, and other people have found some that have been fixed and have been improved. And government want people to use it. They're actively seeking people to use this model. So get on the model, get some buildings built, and see what it chugs out at the end. But what are we going to end up building? I don't know. But I think what people do need to get into, Darren, is what data they need to put in, because it's you've used it. It's heavy. There's Absolutely. A lot of menus and there's a lot of stuff. There's a lot more boxes to fill than there is under SAP, even SAP 10. So I think that the industry needs to kind of get an understanding of what goes in. I think what comes out of that model ultimately now is a series of graphs, internal temperatures and things like this. I think there'll be a lot more to come out of that model, and a lot more interesting stuff to come out of that model as well. The government talks about using wrappers. So a wrapper for future homes to see if the building complies. There might be a wrapper around retrofit, to add different things. And all a wrapper is something that surrounds this model and either takes something from the inputs or the outputs and presents it in a different way. And that actually is a fantastic use of a model. SAP was always behind this closed door. I know people who spent months, years re-engineering SAP into spreadsheets so they can do this work, so they can tap a few buttons and it'll tell you what difference a heat pump makes or something like that. And I think that if that system's opened up, which the mood music is that I think that will happen, that's massive benefit for us as users of it is to, you have a client that says, well, what if we change to a dynamic tariff? What if we I don't know, have an EV charger installed? What kind of things, what difference does it make? And you can just use a wrapper to kind of analyze that without feeding it all back in. Obviously, we made some moves last month about the data becoming available for EPCs and be able to swap it and things like that, which is great. But there's going to be a lot more data in HEM that we can make good use of. Models, sometimes I have a problem sometimes with models being misused, and sometimes they're not very good. But a good model is really useful. And I think good stuff in, good stuff out, crap in, crap out. That's how models work, unfortunately. But if you've got good things going in, you can do good things with it, and I think it's a big adventure that we're all going to go on in the next 5 years.
Good. Do you think we'll hit the deadline?
I don't know. Do we usually hit deadlines on energy modelling? You answer. So I don't know. It's a big move, isn't it? It's a big move. Listen, there's a beta model out that we're already using. We've been asked to do some work on how the model works with our houses in the chamber and things like that. The government are making good progress as far as I'm concerned. There's a model there that I can use and it's kicking out data and it's working. Great. I'm happy with that. There'll be cloud provisions coming up and stuff soon, apparently. It's going as well as I've seen projects go. So yeah, listen, sometimes you've got to be an optimist as well. There's people that will argue with me, but I'm hoping for good things out of it. I think it's a positive move.
Well, Richard, I think we're now in a position where we can go to the demolition zone. We are in the demolition zone. Okay. And Richard, you've created this piece of artwork here, and it's impossible for me to describe, to be honest, for those that are listening. But if you're listening, you need to just go onto YouTube and look at this, because that's the only advice I can give. But anyway, what does it represent?
I think masterpiece would sum it up, Darren.
Yeah.
Or a random collection of blocks stacked on top of each other. What does it represent? I think we hear a lot of bad press about energy savings measures, and I didn't think it used to always be that way. We hear some good press, but there's a lot of sectors that kind of want to pan what we do in terms of energy savings, and they want to badge it as carbon taxing and things like that. To me, it's about people living in better homes. And why pay a fortune for energy bills when we could be spending it on things that we like? Whether it's leisure, whether it's doing other stuff that's a bit more sustainable, whether it's buying the kids toys or whatever it is. It's why would we want to waste stuff? And it's never really sat right with me. Energy savings can be done for really good reasons, and they can be done cost effectively as well. And I think this myth that I think we're busting here is that energy savings can be good, and they shouldn't always be seen through negative eyes. And I think most people would agree with that these days, to be honest. We're all suffering because we don't have a lot of money. And let's not waste it. Like I said earlier, let's not heat Manchester. Let's just heat our homes and keep comfortable and warm for not a lot of money.
I love that. The slogan from Richard: let's not heat Manchester. Oh, yeah. Let's heat the home.
Yeah, I think that's right. That's right.
Good. Well, you are now free in your own way to bust that myth.
This is just me knocking it down, is it? Do you want me to do it from here? I can stay on camera and just throw my pad at it, or I think we should just knock it down with reckless abandon. Nice. I think that's cleared the table quite nicely.
Wipe of the book. Richard, the things that you are doing, not only groundbreaking because you've got two, big chambers that world first. So you're doing great work there, you and your team and the people that work with you.
Thanks.
I'm grateful for what you do personally. Yeah. I know that those people that will be listening to this will be as well. And we will put a load of things down in the show notes that people can click on and look at this even further. But thanks for what you do. Keep doing what you do.
I will, but I'd reiterate, it's a team effort. I'm sat here, but, I would have liked to bring 20 members of the team down. The temptation is we are seen as a facility or a collection of facilities. Facilities don't run themselves, they don't build themselves, and they don't carry out the tests and have the brains. And I think without the brains and the skills that we've developed over kind of 14, 15 years, then it would just be a box with some houses in it.
Richard, it's been great having you on the podcast.
No, thanks for having us down. It's been great. Thank you. Cheers, Dan.